Before we dig exactly into the text of the theorem, let's have a nice closer look at what happened in those examples. Maybe the first one. Um, it worked well when x was strictly greater than 0. And what happened, the justification in the end for that is that I could find something that didn't depend on x, a function that didn't depend on x, that depended only on t, with which I could bound up my my initial f of xt. Okay, I bounded this f of xt by a function which happened to be integrable. So maybe you can see the relation with what we talked about in the previous theorem. What I did here was to I found a dominating function. The same way as in Lebesgue dominating convergence theorem, I needed to find a dominating function that didn't depend on n. Here I found a dominating function that did not depend on x. Well, basically, that's going to be the idea. Yeah, what we're going to do is adapt the theorem so that the Lebesgue dominated convergence theorem, so that we find a dominating function that does not depend on the second variable x. Okay, and so it wasn't possible in the case x was equal to 0. We couldn't find a correct dominating function because, well, actually it was equivalent to a non-convergent to a function for which the integral would not be convergent. Okay, and in that second case, well, here we didn't use a dominating function, but the thing is that if you try to find a dominating function that would not depend on x and that would still be integrable for all, well, that does not depend on x, and so that would work for all possible values of x in R plus, you wouldn't be able to find it, because whatever well, you can make this actually as big as you like. You can always find for some value of t, you can always find an x such that this is going to be as big as you like. That's it. That's why well, that's why we can't actually apply the theorem that we're going to see next. Okay, so let's have a look now exactly at how those theorems are announced. Okay, so let's go for these parameter-dependent integrals. So again, as I said, two theorems, one about continuity, one about differentiability. Okay, continuity and differentiability. So the first thing that should be clear for you is, well, we're going to have a function of two variables, that's f of xt, but then those two variables, one is going to be used for integration and the other one is going to be used for defining a function that depends on the x, which would be just a parameter for the integral. So let's see. What do we need? For fixed value of x, the function that for t gives f of xt is integrable on R. So that's one thing. For some fixed value, well, you've got integrability with respect to t. Okay, so with respect to t. So I think you should also complete the theorems to make it clear where t and x are important. Next hypothesis, for fixed value of t, okay, so now x is going to be the variable that I'm looking at, we have continuity in x. Okay, so the least we could ask is that the inner function is actually continuous in x, otherwise if it's not continuous in x, this wouldn't even have an interesting meaning. Okay. Third hypothesis, this is where we're going to need our dominating function. And of course, our dominating function is going to be, we need that function to be integrable. Okay, so as we integrate with respect to t, our dominating function is a function of t. Okay, and so it has to be just integrable, and of course it's going to be positive if we need this inequality to happen. All right, so how do we say that? We need that for any value of x and for all the t in R, well, which can also always be restricted if you need to restrict that with an indicator function. We need our f of xt in absolute value to be smaller than g of t, sorry. So indeed, that's our dominating function depending on the t, because this is the one we want to integrate. If you remember the example, it meant that we used that to justify the fact that our interval is going to be bounded. Right. So then, if we have those three hypotheses, we have continuity, and this kind of continuity. We can exchange the limit and integral signs, but in terms of continuity in x. Okay? Okay, so that's our first theorem on continuity. The second theorem that is related to differentiability. Okay, so we will want to obtain this kind of thing if we define f of x to be the integral, well, on or whatever you need to restrict it to, of f of xt. So I integrate with respect to t again, so it's going to give me something that depends on x. That's how I'm defining my function capital F of x. What I want is to say, well, f prime of x, by definition, that should be the derivative with respect to x of the previous integral. What I want to do is just to, again, we want to be able to exchange the integral and the limit sign, and our limit actually here just denotes the differentiability sign. So what I want to do is this thing. I want to find a way to write that it's going to be equal to the integral on R of d over dx, which this time it's just a partial derivative. Well, you can keep it straight, because anything that depends on x is going to be related to the first variable. However, we want to be able to write that. So again, what we're going to have is very similar. We will need a dominating function, okay? But we will need a dominating function for this partial derivative, okay? For this partial derivative here, we want to find the dominating function, and the rest is, again, hypothesis that we should check and try to find the logic about the hypothesis that concern the dependency in x and the dependency of the function. All right. So as previously, we need that if we have some fixed value of x, the integral is well defined. Of course, that's the least we can ask. Then we need, of course, the function to be differentiable in terms of x. Otherwise, I wouldn't be able to write that. Okay, that seems pretty straightforward. And finally, we need an integrable function, a dominating function, again, but it's going to dominate the partial derivative in x, right? So we need a dominating function, which means a g function that is going to depend only on t, all right, again, that would be integrable and, of course, positive, because it has to be bigger than the absolute value of the partial derivative, okay? So for all values of x, I can find a unique dominating function that depends only on t, right? And then I can apply my Lebesgue. Well, it's just applying the convergence theorem, actually, right? And so this is our conclusion. Then the derivative of f, capital F prime, is just the integral of the derivative. Okay, let's see some simple examples for well, one simple example for the parameter-dependent integrals. Okay, so let's take a nice one. Let's consider our function f of xt is equal to e of negative t sinus of x times t. Okay. And I want to define my function capital F of x, which is going to be the integral on, let's make it r plus of e of minus t sinus of xt x times t dt, right? So I want to study continuity of capital F on, well, let's say R for all values of x, and differentiability. Right, so let's see what we can do. So we're going to apply those theorems. First of all, for fixed value of x, what about the boundedness of this integral, e minus t sinus of xt dt from 0 to plus infinity? And here we nearly already see what we're going to use later on. Well, of course, this is going to be bounded. Why? Simply because I can bound above my function by, that's going to be smaller than the integral of e of minus t dt, which of course 0 plus infinity, which is equal itself to 1. So that's bounded. Okay. Do I have that for all t? Do I have that the function x e minus t sinus of xt is continuous? Yes, indeed, because I'm just composing, multiplying continuous functions. All right. Do I have a dominating function? So again, a function that depends only on t and that is integrable for all value of x. Well, x we said should belong to R. Okay, yes, we do. We've already found it. We said, well, we used it a bit earlier. We just used the fact that the sinus is anyway smaller than 1, so that this is smaller than exponential minus t. Excellent. And of course, this function is integrable, right? We already said it was small. It was equal to its integral on R plus. So we can conclude using the theorem on parameter dependent integral, f is continuous on R. Okay, and similarly, if I wanted to well, just on that point, that means, for instance, f of 0, if you plug 0 in your function, you get the integral of e minus t times the sinus of 0 times t dt on 0 plus infinity. So the sinus is 0, so that should be equal to 0. And indeed, the theorem tells you that if you take the limit of, as x tends to 0, of that stuff, e minus t sinus of xt dt, well, you're going to get 0. That's continuity. Okay, well, try to apply the same stuff on the same function, but for differentiability.